Okay, in the previous video, we learned about how to make epoxides. Now we're going to see what types of reactions epoxides undergo. And these primarily are categorized as ring opening reactions. It's actually split into two videos. This video is a little bit longer, and so the examples are separated into a separate video. I think I mentioned in a previous video that most ethers aren't very reactive. However, due to the significant ring strain in epoxides, they're actually very reactive. And this makes them extremely useful as synthetic intermediates. Now, what I mean by ring strain, if we think about what oxirane and these other epoxides look like, right? The oxygen and the carbon atoms that form this ring are all sp3 hybridized. And being sp3 hybridized, they want bond angles of about 109.5. Right? But when they're in this three-membered ring structure, their actual bond angles are something closer to 60 degrees. Right? And so this deviation between what they have in terms of bond angles and what an sp3 hybridized atom would actually like to have is quite large. And so this is what gives rise to the ring strain. And so epoxides are reactive to a wide variety of nucleophiles. We've seen all of these before in other reactions, but they're reactive towards Grignard reagents, hydride reagents, alcohols, alkoxides, water, and so there are a lot of things that we can react these epoxides with. So we're going to consider two general types of reactions, of ring opening reactions that these epoxides can undergo. The first ones we're going to consider are reactions with strong nucleophiles. So hydroxide is an example of a strong nucleophile, and so this is a two-step mechanism. It's characterized by a nucleophilic attack and then a proton transfer. And so the first step is an SN2 reaction where we have a concerted ring opening mechanism. So the hydroxide attacks, and then this bond between the carbon and oxygen becomes a lone pair on the oxygen. That leaves us with a negatively charged oxygen, and to finish up the reaction, we generally have to react this with a proton source. Water is often a good choice, and so we finish up with a proton source where the negative oxygen steals a proton from water, and then we make a hydroxide. Now, when we first learned about substitution and elimination reactions, right, we learned that, essentially OH, or a neutral oxygen, is not a good leaving group because OH minus is a strong base, so it's not a stable base, so it's not a good leaving group, right? In these ring opening reactions, this mechanism we just saw, essentially we have that exact thing. When we open this ring, we're forming a negative oxygen, right? Now, the reason that these ring opening reactions can still happen without first having to protonate that oxygen is due to the thermodynamics, right? So a normal ether or an alcohol is relatively stable. And so if I try to have the OH or the OR as the leaving group, right, that alkoxide that we form is less stable than the ether, and so that reaction doesn't really want to happen, right? But because the oxiranes or the epoxides are so unstable due to that ring strain, right, they're actually higher in energy than the alkoxides that we're going to produce, and so that's why we can have these ring opening reactions with this neutral oxygen that normally, when we first learned about substitution and elimination and leaving groups, we didn't see. We always had to protonate that oxygen first. Because of the ring strain of the epoxides, we don't have to protonate it first in order for it to be an okay leaving group. So we saw an example where OH minus was used as the nucleophile, and we can use a lot of different nucleophiles, strong nucleophiles, to open up these epoxides. So we can use alkoxides, right, where our nucleophile, right, the sodium is just a counterion, right, we're really interested in the RO minus, and so that's going to make, right, the OH from the epoxide, and then we're going to add the OR. Or cyanide ion is also a strong enough nucleophile, and so that'll add a CN and then the OH from the epoxide. Or we can use SH minus, where we're going to add an SH and then the OH from the epoxide. We can use Grignard reagents, where we're going to add an alkyl group as the nucleophile, or these hydrogen sources. So LiAlH4 is going to add a hydrogen as a nucleophile, right? H minus is acting as the nucleophile in that case. All right, so next we want to look at the regioselectivity and the stereoselectivity of these ring opening reactions. Okay, let's talk about regioselectivity first. Generally, when we think about SN2 mechanisms, we know that it prefers methyl substrates, then primary substrates, then secondary substrates, and then generally tertiary, we don't see reactions with an SN2 mechanism at all. And so when we think about which of the carbons of the epoxide that the nucleophile is going to attack, right, if we think about this carbon, right, the O is the leaving group, so there are 3 other carbons attached to this carbon, so this is tertiary. This is the leaving group, so it's only attached to one other carbon, so this one's primary. So our nucleophile would prefer to attack here rather than here. And so our nucleophile is going to attack here, and we're going to open it here, and so the OH ends up on the more substituted carbon. And the nucleophile ends up on the less substituted carbon. All right, in terms of stereoselectivity, this is also what we would expect for an SN2 mechanism. And so, I have this carbon center that's not being attacked. I have this carbon center that is going to be attacked. So the stereochemistry here is not changed. The OH remains on the wedge and the methyl remains on the dash. But this is where our nucleophile is going to be attacking. And if you remember, for SN2 mechanisms, we get inversion of configuration. And so we see the same thing in these ring open reactions as we would expect for typical SN2 mechanism. All right, so previously in this video, we've been looking at ring opening reactions involving strong nucleophiles, right? We can also open up these epoxides with weak nucleophiles, but this needs to be done in acidic conditions, and so these are going to be acid-catalyzed reactions. And so the weak nucleophiles by themselves can't open up these epoxides, but if I do it in acidic conditions, then the acid can help catalyze this reaction and get it to go. So there are kind of 2 types of reactions that we'll see under acidic conditions. One, when reacting these with HCl and HBr, the Cl- and the Br- are actually good nucleophiles, but because of the presence of these being strong acids, these are going to be in acidic conditions, and so the mechanism is slightly different than we saw last time. And in fact, the steps are backwards than what we saw before, right? With the strong nucleophiles, not in acidic conditions, right, first we saw the SN2, then the proton transfer. Under acidic conditions, these happen backwards, right? So first we get the proton transfer, where we now have the positive oxygen, then either the Cl- or the Br- attack with an SN2 mechanism. All right, so not only can we use HCl or HBr, but if we're in acidic conditions, I can also open up these epoxides with weak nucleophiles like water and alcohols. And so generally the source of the protons, the acidic protons, is sulfuric acid. And so first we'll get the protonation, and then the water or the alcohol can open up that epoxide. But let's take a look at that mechanism, because there's an additional step when we have these neutral weak. Right, so both in the first examples when we had the strong nucleophiles, or when we had HCl or HBr, the nucleophiles that were attacking were themselves negative. Now the nucleophiles that we have attacking are neutral. So the first step is the same as if we were reacting this with HCl or HBr. First we have a proton transfer. In this case, our proton source is going to be hydronium ions. Right, then the second step is the same as it was for HCl and HBr. The nucleophile attacks, it opens up the epoxide, right? But because this nucleophile was neutral, right, we have this cation, right? And so we need a final deprotonation step, a proton transfer, where we'll have water come in and deprotonate our intermediate. Now, there's one big difference between the regiochemistry of the reactions with the strong nucleophiles that we looked at first and these acid-catalyzed ring opening reactions. So as long as we have primary or secondary sites that can be attacked, what we would expect for an SN2 reaction is the same. We're going to add the nucleophile to the less substituted carbon. However, if a tertiary carbon is present, then the nucleophile attacks in a counterintuitive fashion, and it actually attacks the tertiary carbon, which we generally would not expect for an SN2 mechanism. So on the next slide, we'll look and see why we get this very unusual result. And so our argument for why the nucleophile would attack at the less substituted carbon was based, and every time we've talked about it, specifically on steric effects. Right, when that nucleophile comes in, if we have a more substituted carbon, it's harder for it to get in, and so it's always going to attack the less substituted carbon. But steric effects aren't the only thing that influences these reactions. We also have electronic effects that we need to consider. And so because this oxygen is already protonated, some of that positive charge is going to be distributed to the carbon atoms that are also part of the epoxide ring. And as we know, carbocations, right, positive charges on carbons, are more stable the more substituted that carbon is. And so when we protonate this epoxide, it's not perfectly symmetric when we have this tertiary carbon as part of the ring. And because the carbocation is going to be more stable here, this is going to have more carbocation character, where in a carbocation we have 3 bonds and no lone pairs. And so this bond is already largely broken when we protonate this epoxide. And so then when the nucleophile comes in, there's more positive charge associated with the more substituted carbon, plus the more it looks like a carbocation, the more planar it's going to be. And so the nucleophile has an easier time to get in here than we generally see with SN2 reactions. So these are what we call electronic effects. And so when we have only primary and secondary carbons that are part of the epoxide, then what we generally expect based on steric effects, the less substituted carbon is the one that's going to be attacked by the nucleophile. When we have a tertiary carbon that's part of our epoxide, that's where the nucleophile is going to attack because of these electronic effects that we talked about. So this is a big difference between all the other SN2 reactions that we've looked at so far, but we're going to see these electronic effects more and more as the semester progresses. And so we have to balance the steric effects that we've talked about to this point when thinking about SN2 reactions and these electronic effects that may also occur. Okay, finally, when we think about the stereochemistry, fortunately that is the same as we would expect for an SN2 process, and we do get inversion of configuration, right? So the methyl is on the dash because this carbon is tertiary. We're going to attack here instead of here, and so we do still get the inversion of configuration in this SN2 process. So I've got another video where we're going to look at some examples of these ring opening reactions. So I highly encourage you, either watch that video or definitely work the examples in the textbook, or ideally do both. I think that these are the hardest reactions that we've learned this semester, and I didn't really get comfortable with these until I'd worked a bunch of the example problems.